Email from a retired F-16 pilot whose name is Mike. His new YouTube name is FE Viper 16. A good name, so watch for him in the comments. I spoke to Mike on the phone today, but he wishes to remain anonymous, and I will certainly honor that. Again, if you are a professional and would like to talk to me about the unique perspective of the flat earth related to your expertise, please email me at tabooconspiracy@gmail.com. I will always keep your information confidential if that is what you want. I do hope this information will lead to more flat earth investigations because these radar systems and the aircraft using them are fascinating, and the flat earth evidences they introduce are indisputable. I wish I could share my full discussion with Mike because it was awesome, as this retired Air Force pilot confirmed that he definitely flew over a flat and stationary Earth and that none of the systems of his aircraft were designed with the curvature in mind. Now, I might make some mistakes here, and I do apologize for that, as the information was complex for me, but Mike did say that he might stick around and answer your legitimate questions in the comment section. An F-16 can fly up to 1,500 miles per hour, and may be intercepting another craft flying in the opposite direction at the same or a different altitude at similar speeds. Breaking it down, 1,500 miles per hour is 250 miles in just 10 minutes. As Mike discovered, the paramount problem with the globe is 8 inches per mile squared. The infamous and quite accurate formula that calculates the alleged curvature drop if the globe were real. That easy to understand formula absolutely destroys the globe because no one has seen or accounts for that insane amount of curvature drop ever. But for an F-16 flying at 1,500 miles per hour, that would be a curvature adjustment of approximately 42,000 feet in just 10 minutes. But no pilot makes that ridiculous curvature adjustment. But think about the problem when an F-16 is quickly intercepting another aircraft coming from the other direction. Consider the unbelievable amount of curvature adjustments that would be necessary for an Air Force pilot on intercept. And yet, Air Force pilots never learned about the curvature drop in training or otherwise, as confirmed by Mike. What's also fascinating is the fact that Air Force pilots learn and experience it daily that when a distant aircraft is at the horizon, it is at the same altitude. If the distant aircraft is above the horizon, then the pilot knows the aircraft is higher. And if the distant aircraft is below the horizon, then the aircraft is at a lower altitude. I think this photograph shows what I'm talking about. You can see which balloons are higher and lower based on the horizon line. There's more proof that the horizon does indeed rise with eye level, which is an absolute impossibility under the globe. But getting back to the non-existent curvature adjustments, the globe propagandists would probably answer that the aircraft automatically adjusts because of some magical force of gravity, automatically pulling the nose down of the aircraft to strangely maintain equal altitude, or that the varying air pressure densities keep the aircraft at the same altitude. I've heard both of these silly explanations, but that brings us to Mike's information. This is with respect to the AN/APG-68 long-range radar system. It has a range up to 184 miles. Here's a picture of what the operation screen looks like in the cockpit of an F-16. This will make more sense in a little bit. Essentially, as an F-16 pilot, Mike would fly with a wingman or maybe 3 other F-16s in formation. Each pilot, using his radar system, would then have the responsibility to sweep a key portion of the sky in front of the aircraft based on the F-16's position. This is for maximum efficiency. For example, if there were 2 F-16s in formation, the one on the left would sweep a section of the sky on the left. The F-16 on the right would sweep a section of the sky on the right. Makes sense, right? These aircraft don't sweep the entire sky, but only a key angled segment of the sky, like 60 degrees up, 60 degrees down, 60 degrees to the left, or 60 degrees to the right. So if, say, 4 F-16s are in formation, one pilot may have the duty to sweep his radar looking for aircraft at 10,000 feet and above on the right side. Do you see the problem yet? What is a radar sweep at 10,000 feet on the alleged globe at 80 miles ahead? Because 10,000 feet at Mike's point of view would not be 10,000 feet 80 miles ahead at the enemy's position. In actuality, that aircraft would be much higher than 10,000 feet than what the F-16's radar would indicate if we lived on a globe. Instead, the computer radar system is based on a flat map. None of the radar readings would be accurate, and enemy aircraft would exploit these problems all the time if we lived on a globe. Just think about it. How could you lock, track, and acquire an enemy aircraft when the height curvature adjustments would throw the whole matter into disarray? Here's a short 4-minute clip from an online tutorial for an F-16 simulator that talks about how the F-16 radar system works. But I think it'll help you understand Mike's information, but you're welcome to skip ahead 4 minutes if you're impatient.
We are positioned here, looking that way. Range 0, a quarter, half, 3/4, full. And that depends on our range scale here. So if we were on 80, that's 80 miles, 60 miles, 40 miles, 20 miles. If we were on 10 miles, 10, 7.5, 5, 2.5, and so on. So currently azimuth is 6. This is the width of the slice of cake, the width of the scan zone. That means 60 degrees to the left, 60 degrees to the right. If we now go to A3, it's now 30 degrees to the left, 30 degrees to the right, total 60 degrees. The limits are shown by that line there and that line there. Now if I were to move my cursor off the edge, you can see it follows where I go to the max limits of the radar. The bump stops, they're called, 60 here, 60 degrees there. If we want to go again, we can go to 10 degrees, 20 degrees total. And you can see we can move left and we can move right all the way to the bump stops. Let's put it back on 60. At this point you might think, well, why would you not always have it on full width? Well, the reason is because of the refresh rate with the B sweep. That is the B sweep at the bottom there, going right and left and right and left. Remember, every time it hits the bump stop, it goes down a notch. Hits the bump stop, goes down a notch in terms of elevation until it's finished its bar, its elevation bars. The bigger, the wider you scan and the more bars you have, the bigger your refresh rate is, the harder it is to keep contacts on screen. And it is an absolute art form to keep contacts on screen and balance your situational awareness with your ability to see and track targets. So that's azimuth. Now we have our elevation, the thickness of our slice of cake. How many bars do we want it? Remember, each bar is about, it depends on different radars. They're usually about 3 to 5 degrees. We've got 4 bars at the moment, so that means 4 bounces between bump stops, 4 B sweeps before it resets. We can have 1, we can have 2. So this will give us the maximum size elevation, this will give us the smallest size, this will give them the medium size. But the bigger the size is, the lower the refresh rate, the harder it is going to be to lock, track, acquire, and keep a track of these targets. Okay, M3 doesn't do anything at the moment. So next we've got our carrots. We've got our azimuth carrot, or our B sweep. That's this guy here. That is where the antenna is pointing. 60 degrees left, 60 degrees right is where the bump stops are. This is our elevation, so that you can see it will go down in 4 bars, then back up to the top. And this radar can handle 60 degrees left, 60 degrees right, 60 degrees up, 60 degrees down. So this is 0 degrees azimuth, this is 0 degrees elevation. That is up there somewhere, 60 degrees up, 60 degrees down. If we want to change our avatar elevation, then I'm going to press the button and we can move it up here like that. And down, want to move it down, whoops, wrong button, we can move it down there like that. Look how, if I aim it down, these contacts disappear. These contacts have disappeared. They're now fading. And that's because my slice of cake is aimed too far down and it's below them. If I want to regain them, because I know they're roughly co-altitude, then I move to the middle and we'll start picking them up after a couple of sweeps. Okay. Now, I know what you're thinking. I can know what angle this elevation is set to, but in real terms, what actual altitude is that set to? And that's where these 2 numbers here, you'll be using these 2 all the time. Note that wherever I move this cursor, these 2 numbers change. You will always be looking at them. What they are saying is, at the range that I've got this cursor set, which currently is 40 miles. Remember, we're on 80 miles there, so 80 miles there, 0 miles there, 40 miles there. At 40 miles, if I drew a plumb line, that is a vertical up to down line, through our slice of cake, our scan zone, at 40 miles distant from me, it would intersect, that plumb line would intersect the top of the scan zone at 54,000 feet ASL, and at the bottom minus 5,000 feet ASL theoretical.
I don't want to bore you much longer, so let's get to Mike's email. I have a bit of knowledge from my days as an F-16 pilot that I need to share with someone. I respect your work and thought you might be another great person to pass this to. I don't have, nor do I want, a platform, so here you go. If you decide to verify what I'm telling you and have questions, feel free to contact me here. This will be tough to illustrate with words, but I'll try. The F-16 has a radar called an APG-68. At least it did 18 years ago when I last flew it. The radar, in air-to-air mode, has the ability to scan forward plus or minus 60 degrees of the nose, 120 degrees, plus a back-and-forth elevation selectable of 1, 2, or 4 bars or rows. In other words, in one bar, it simply sweeps level relative to the aircraft bank back and forth at the same elevation. In 2 bar, it sweeps all the way, then drops a certain amount to sweep back, thereby doubling the volume of airspace searched. In 4 bar, it does the twice, doubling it again. Think of the radar beam as pointing a flashlight. The elevation of the sweeps are pilot controllable. The pilot can tell what the elevation of the sweeps are in the display. At the cursor position, the top and bottom altitudes of coverage are displayed at the range of the cursor, and this altitude is controllable with the L strobe, a little wheel on the throttle. We use this because if my search responsibility is 10,000 feet and above, I can roll up and cover my area more efficiently. I know this is probably clear as mud, but bear with me. Obviously, you can determine the width of the sweeps at various ranges of your search. In other words, the distance between the sides of your scope. If I run the cursor out to 80 miles, isosceles triangle math gives you 138 miles from side to side. Curvature math gives you a hump on my nose of 12,700 feet. In other words, if I roll up to search 10,000 and above and set that in the center of the scope, I'd be 22,700 feet and above on the sides of my scope, right? Well, non-practice. If I run my cursor out to any distance, the display shows the same on the left side, middle, and right. So my conclusion is the engineers are going to get fighter pilots shot down because they didn't take into account the curvature of the Earth, bastards, or the Earth is flat. That's it. That's Mike's email. I hope that was semi-understandable. The globe simply doesn't exist in reality, and now we have a retired F-16 pilot who confirms the same.